In this video, we'll finish looking at our addition reactions to alkenes. So far, we've looked at adding halogens, adding alcohols, making alkanes, cyclopropanes. Now we're going to focus on 1,2-diols, carbonyl compounds, and epoxides. First, let's start with epoxides. Epoxidation is the formation of an epoxide. What it is it's really an oxidation of our compound. So an oxidation is a reaction that results in the loss of electron density for a carbon. So you can think of it as a bond formation between a carbon and a more electronegative atom. Or you can think of it also as a bond breaking between a carbon and a less electronegative atom. And so alkenes can oxidize to give epoxides when we treat them with peroxy acids. So remember, an epoxide is a cyclic ether with an oxygen atom in the 3-membered ring. So our epoxides look something like that. And so what happens is we have our double bond and it reacts with our peroxy acid. One typical peroxy acid we use is called MCPBA. So MCPBA, metachloryl peroxybenzoic acid, looks like this. And this is a really common epoxidizing reagent. Now, looking at the mechanism, when we first form the epoxide, what's going to happen is our double bond is going to come and attack the second of the oxygens for the peroxide part. That's then going to cause the electrons between the two oxygens to move over to the electrons between the oxygen and carbonyl. Electrons from the carbonyl then go and grab a hydrogen, which then allows those electrons to move over to the alkene. So if we look at the transition state, we can see it's kind of a cyclic transition state within the peroxy acid part. And then the alkene is on the end grabbing this oxygen off. So once it grabs it off, we end up with our epoxide and a carboxylic acid. And then epoxides are useful intermediates for creating 1,2-diols. And so this is also considered our epoxidation ring opening. And we can do it 2 different ways. We can have an acid catalyzed ring opening, and we can have a base catalyzed ring opening. So let's first look at the acid catalyzed ring opening. So our acid catalyzed ring opening involves our epoxide and our acid catalyst, which gives us our product. And it does this in an anti-addition fashion. So the 2 diols add anti to each other. Or we can consider this an anti-dihydroxylation. And so looking at the mechanism for this ring opening, if we start with our epoxide and we have our acid, what'll happen first is the oxygen from the epoxide will get protonated. That protonation will then result in a water molecule, which will then come and attack our epoxide. And this results in the opening of our ring. then have to remove the hydrogen from the water that just attacked the epoxide. So a couple things to note. Our water molecule attacks from the back side. It doesn't attack from the side that the epoxide's on, it attacks from the opposite side. That's how we end up with our anti-addition. That's how we end up with the two alcohol groups opposite of each other. And then there's a couple things to note about the addition and what happens. Depending on the substitution of the carbon, you could end up with this water molecule attacking either side. So when we look at that, if we compare this epoxide to this epoxide, we can end up with slightly different products. So this water, it'll end up attacking this side of our epoxide. So if we draw these as a different color, over the course of the reaction, we'll end up with it on that particular carbon. And in our second example, we end up with the alcohol on that carbon. So let's think about what's the difference between these two examples. In the first one, we have a tertiary versus a tertiary. In the second one, we have a tertiary versus a primary. So you can see when it's tertiary and tertiary, we're going to go for the less bulky side because it's easier to get to. When it's tertiary versus primary, we actually end up going towards the tertiary side, the more substituted side. And so when we're looking at this, if we want to compare different sides, so let's say we have a secondary versus a primary. So one alkyl group versus none. We're going to substitute on the primary. If we have a tertiary versus a secondary, we're going to substitute on the tertiary carbon. And we'll learn why a little bit later in the course. But we can use one other thing. We can use other acids. We don't just have to use H3O+. So we can use HBr, or we can use HI, or HCl. What will happen when we use these other acids, instead of adding a water, we can add a bromine, or we can add an iodine, or we can add a chloride. So we can use some other acids besides water, and we can add different things. So if I take that second one, and I used HCl, now what'll happen is that chlorine goes on the more substituted side, and the alcohol is on the less substituted side. So this is one way we can open epoxides is to use acids. The second way we can open epoxides is to use a base. So these are going to be our base catalyzed openings. And in bases, it goes through a slightly different mechanism. So if we have our epoxide and I have my base, it's going to be in water, and we also need to add some heat. Since it's in base, the first step is going to be that negative charge is going to come and attack the less substituted side. So our less substituted side gets attacked. That'll then move electrons up to the oxygen. Our product that looks like that. Then we're going to have to neutralize that negative charge. So we use water for that negative oxygen to come and grab a proton to create our dihydroxylation or our diol product. And we can still see we have that anti-conformation. So with these base openings, we're always going to attack the less substituted side in a base catalyzed opening of an epoxide. And so that means when we do our reactions, let's say we wanted to compare our base catalyzed to our acid catalyzed, and we use an O18 isotope to do isotope trace. What'll happen is that O18 will end up on the less substituted in the base reaction. And in the acid, if we do the same thing, but now our acid oxygen is the O18 isotope. We end up with that O18 on the more substituted side. So we can see they go through different mechanisms because that isotope ended up on a different carbon in a different position. So it's important to know the mechanism and which mechanism you want to go through. So now let's talk about our syn dihydroxylations. We've seen how to add the alcohols when they're on the opposite side, but if we want the two alcohols on the same side, we have to go through a different process. And in this one, we're going to use osmium tetroxide to form a syndiol. And so what happens with the osmium tetroxide is the osmium has its two alcohols, has its two oxygens coordinate with the double bond. So you create a cyclic osmate ester. That then gets reduced and taken off with our sodium sulfite and water. And so we end up with our syn diol. So one important thing about osmium tetroxide, it is expensive and it is extremely toxic. It has an exposure limit of just 2 micrograms per cubic meter of air. If you have more than 2 micrograms per cubic meter, you now have a lethal dose. One way I've heard it described is if you can smell it, you have a lethal dose in you. So because it's extremely expensive and toxic, conditions have been developed where the osmium tetroxide is regenerated after the reaction. So you only need a small catalytic amount. This reduces the chance of getting a lethal exposure. So as long as it's in a catalytic cycle, you don't need much at all. You can actually use less than the exposure limit. So you have your alkene, and then we can use NMO or N-methylmorpholine N-oxide as our catalyst that helps regenerate the osmium tetroxide. And doing it this way, where we have a catalyst to reoxidize and regenerate the osmium tetroxide, you can still end up with about a 60 to 90% yield of your syn dihydroxyl product. And it goes through that syn addition because we're adding 2 oxygens to the carbons at the same time. But let's say you don't want to use the super toxic osmium tetroxide. Another one we can use is potassium permanganate. It works similar to osmium tetroxide, but it's more reactive. So it still does a syn hydroxylation. The only thing is, in this case, it has to be under very mild conditions and cold temperatures. So it still does that syn hydroxylation because we're still adding the 2 oxygens at the same time. So you're not going to isolate the intermediate here. Instead, it's going to get removed and removed to form your diol. So if we were to write this reaction out on an arrow, I would say it's potassium permanganate, and it's usually in dilute conditions with cold water because we need those mild conditions to get us from our alkene to our diol. Now let's say we're doing this reaction, but we forgot to cool down the water. So we added warm water instead. Or we didn't really dilute the potassium permanganate because we thought we didn't need to. When you do any of those, use a warm solution or an acidic solution or something too concentrated, you're actually going to end up with an oxidative cleavage using that potassium permanganate. So what'll happen is if we use our potassium permanganate when it's warm and concentrated, so warm water concentrated, instead of that diol, it's going to keep oxidizing and split your double bond in half, giving you carbonyl groups. So it'll give us a ketone and a carboxylic acid. So you can see your carbon groups from one side, get the carbon groups of another, and the carbon groups here are now here. And anything with a hydrogen, those hydrogens get replaced with alcohol groups. So that's how we end up with carboxylic acid here. And so potassium permanganate is a very powerful oxidizing reagent. It's a very powerful oxidizer. Given the chance, it'll keep oxidizing anything to its highest oxidation state. So even if we started with an aldehyde and we did potassium permanganate, it's going to turn that aldehyde into a carboxylic acid. It's going to oxidize whatever it can oxidize. Let's say we're doing this reaction with our compound. We want to do the cleavage, but I don't want to end up with carboxylic acid. What if I want an aldehyde instead? If I wanted to leave that hydrogen alone? To do that, we're going to do oxidative cleavage, but with ozone. So doing an ozonolysis. So this is where we can take our alkene and split it apart in a more mild fashion. So I can have my alkene, and I can do ozonolysis. And I'll still do an oxidative cleavage, but instead of forming carboxylic acid, now it just forms an aldehyde. So it's a more mild than the permanganate. And if we remember, ozone is O3, where it exists as two resonance hybrids. And looking at the mechanism for our ozonolysis. Now looking at the mechanism for ozonolysis. We start with our alkene. It's going to react with the ozone. And so it reacts to give this ozonide intermediate which then that ozonide intermediate goes through rearrangement and cleavage using our sulfur with the two methyl groups to give us our product. And then we end up with DMSO as one of our byproducts. So we can use our dimethyl sulfur, or you can also use zinc in water. That's another one that can do this cleavage and do the second step. And as I said, this has the benefit of being milder than the potassium permanganate. So you're not going to oxidize everything up. You're just going to cleave the double bonds. And you can see it still has your two alkyl groups here, just like we started with. One alkyl group here, just like we started with. And then that hydrogen that's up here remains in our product. And so now we've seen how to make all of these different compounds and all of these different functional groups starting with just alkenes.